In today's video, we will be discussing thermodynamics. More specifically, the second law, entropy, and Gibbs within the AQA A-level chemistry course. Starting off with entropy. It's defined as the measure of disorder of a system. So the more disordered this system is, the greater the positive value of entropy. On the left here I've got a graph that plots temperature on the x-axis against entropy on the y. We can see that as temperature increases, so does entropy. And as we go through the phase changes, we see that solids are the most ordered and have the lowest value of overall entropy, and gases the highest. This can be explained in terms of freedom, which is another way of looking at disorder, and that is if the molecules are free to move with their kinetic energy within their system, they are more disordered. I've got some self-test questions up at the top here, designed to test your knowledge from classes and from revision. Please pause the video here, try the questions, and then unpause me. Okay. Number 1, why does entropy increase as temperature increases? So as we increase in temperature, if we look at this gas box here for example, if we increase the temperature, we'll increase the energy of each of these particles in the system, and therefore they will move about faster and have greater disorder. This means we see an overall increase in entropy. How can the overall entropy change for a reaction be calculated? Well, delta G, delta H, and delta S are all state functions. This means that you can calculate the change in their values, provided you know how the system started and how it finished. So if you have A plus B goes to C plus D, so long as you know the delta S of the reactants and the delta S of the product, you can do delta S products minus delta S reactants to give you your overall delta S of the reaction. This applies also and equally for Gibbs and enthalpy. Gibbs free energy change is defined as the enthalpy minus the temperature times the entropy change. Usually we'll quote answers in kilojoules and mole. The graph on the left here is common to see in past papers for the A-level spec. It plots temperature against Gibbs free energy, where the plot is y equals mx plus c in a linear form, and if you did A-level or GCSE maths, you'll know that the gradient here is equal to y2 minus y1 over x2 minus x1, which is commonly how you calculate it in past paper questions, and that will give you minus delta S. Don't forget that negative sign, it's a common trip-up point. The most important thing with Gibbs free energy in regards to doing past paper exam or exam questions is understanding what delta G represents. It's the feasibility of a reaction. When delta G equals 0, this is a reaction at equilibrium. I've highlighted here this point in the graph, and this represents when delta G equals 0. When delta G is negative, this reaction is feasible. Now, a feasible reaction does not mean it will go spontaneously or it will go instantly, or there might be a high activation energy. It simply means it is possible. However, a Gibbs free energy of greater than 0 is non-feasible. This reaction will not and cannot go. I've got a little note down at the bottom here saying both Gibbs free energy change and entropy can be calculated by this given formula. I discussed this on the previous slide when talking about how we would calculate entropy from products and minus reactants. Looking at this example question, we get given some data and told that it's enthalpy and entropy, and we've been asked a few questions. So why is the standard entropy value for carbon dioxide greater than that for carbon? Well, it's an argument of disorder. Carbon is a solid, as I've drawn here, and this is very ordered, whereas CO2 is a gas, so it is very disordered. So we would expect carbon, that should be carbon dioxide, to have a greater value of entropy because the system is more disordered. Now, state the temperature at which the standard entropy of aluminium is 0 joules per Kelvin per mole. Well, if we're saying that the entropy, the standard entropy, is equal to 0, this must be the most ordered this system possibly can be. Going back to our other graph, we know that as temperature increases, so does entropy. Therefore, the most ordered, the lowest energy of the system, must be at the lowest temperature possible. What is the lowest temperature? On the Kelvin scale, it's 0. 0 Kelvin. Use the equation and the data in the table above to calculate the minimum temperature in Kelvin at which this reaction becomes feasible. Now, as soon as the word feasible is mentioned, immediately it's worth putting down the Gibbs equation. Now, what is the minimum point that a reaction becomes feasible? Well, that's when delta G is equal to 0. Because we have this cutoff point where anything above, where delta G is above 0, is not feasible. Delta G must be that cutoff point, or delta G equals 0. Therefore, we can say that the enthalpy is equal to T delta S, and we're rearranging in terms to find K, so we can put it like so. Now what we need to do is compute both delta H and delta S and plug this into the equation to find our answer. The enthalpy, again, we'll do this via products minus reactants, as I've mentioned in this slide and this slide as well. And that will be 3 times minus 394 minus 1,669 times by 2. And this gives us 2,156 kilojoules a mole. It's important to mention here that the enthalpy of formation of an elemental state is 0. We do the same for entropy, and we will find that we subtract our products, we get 634 joules per mole, or joules per Kelvin mole. Now, we need to put these in the same format, and I'll simply divide this one by 1,000 in order to get our answer in kilojoules per Kelvin mole. When I'm writing per Kelvin mole, I simply mean per Kelvin per mole, for reference. Finally, we'll sub this in to our equation to get an overall value for temperature, where temperature equals 2,156 over 0.634, which will be approximately 3,401 K.